Today we're going to cover section 3.6 in our pre-algebra textbook from BJU. We're going to be learning about the real number system. So to begin, we're going to look at each type of real numbers that exist. The first set is called the natural numbers. And so the natural numbers are our counting numbers. So these are the numbers that when you learn to count, this is what we started with. So the natural numbers, the symbol for natural number kind of looks like an N, but notice how it has a double line right there. And that's our symbol for natural numbers instead of actually writing the word natural numbers. So it's a set. So we're going to use these braces to indicate a set. And then, of course, we're going to list our natural numbers. So that's 1, 2, 3, 4, 5. And then we have these things called ellipses to show that it goes on forever in the positive direction. So natural numbers are only positive numbers, and they don't include 0. And they also don't include any fractions. Our next type of numbers are whole numbers. So whole numbers are very much like natural numbers. In fact, you can define whole numbers as natural numbers with the addition of 0. So the symbol for whole numbers is like a W, except for there are those double lines right there. So that's the symbol for whole numbers. And then again, remember to use your set braces to show that's a set. And then we're going to list our natural numbers, but then just include 0. So now we have 0, 1, 2, 3, 4, and then the dot, dot, dot. So the natural numbers is what we call a subset of our whole numbers, because our natural numbers are found inside our whole numbers. So they are a subset. So everything that's a natural number is also a whole number. Here's a symbol for subset. It almost looks like a C, but it's a little scrunched down, and then of course we have a line underneath it. So this reads, the natural numbers is a subset of the whole numbers. So if we were to draw this out, we would have the set of natural numbers, or this circle, lives inside the circle of our whole numbers. And so everything that's a natural number is also a whole number. However, 0 is a whole number, but it does not live inside the circle of natural numbers. Our next set of numbers are called integers. So integers are whole numbers and they're opposites of the natural numbers. So these are positive and negative numbers and 0. So the symbol for integers you would think would be an I, but it's not. It is a Z, and so it's not quite a Z, though it does have that double line. And for this set, we're still going to use our set braces, but we have ellipses on both sides. We have dot, 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 and then we have our negative numbers, we have 0, we have our positive numbers, and then again dot, 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 to show that it goes on forever in the positive direction, but also in the negative direction. So now we can say that our set of natural numbers and our set of our whole numbers are subsets of integers, because our set of integers includes 0 and our set of integers includes all the positive natural numbers. So we can say that W, our whole numbers, is a subset of Z, or our integers. We can also say that N is a subset of Z, because our natural numbers are a subset of our integers. So now this is what our circles look like. We have our innermost circle, which are natural numbers. So natural numbers are also whole numbers, which are also integers. But then our next circle going outwards is our whole numbers. So our whole numbers includes all of these natural numbers, however it includes 0, which is not a natural number. Our next ring is our integers. So our integers includes all of our natural numbers and our 0, which is the difference between a whole number and natural numbers. But then it also includes all of our opposites of natural numbers, so our negative numbers, so -4, -26, -8. Then we have our next set of numbers, which are rational numbers. And our rational numbers are all of our integers and fractions. So our rational numbers are the symbol Q, but it's not quite a Q because it has these lines, double lines in it. So this is how we define rational numbers. A over B, that's what this is, A over B, so our fraction, right, A over B, such that, that's what this line means here, such that A has to be an integer and B has to be an integer. And remember, integers can be positive or negative numbers. And we're also going to specify a little bit more. We're going to say that B cannot be 0 because remember, B is our denominator and we cannot divide by 0. So since integers make up our rational numbers, we can say integers are a subset of our rational numbers. So Z is a subset of Q. And since W is a subset of Z, our whole numbers are a subset of our integers, that means that our whole numbers are a subset of rational numbers, or W is a subset of Q. And since our natural numbers are a subset of our whole numbers, which are a subset of our integers, which are a subset of our rational numbers, we can say that our natural numbers are a subset of our rational numbers, or N is a subset of Q. So now we have this. So we started with our natural numbers, our innermost circle. Then we went out to our whole numbers, which includes the natural numbers and 0. Then we went out to our integer, which includes the whole numbers and our natural numbers, but then added our negative numbers. And then we went out even further to what our rational numbers are, which included our integers and our whole numbers and our natural numbers, but then added our fractions. So notice how our fractions has 1 over 7 and negative 2 over 7, but it also has negative 0.7 and 2.58. And you're like, well, those aren't fractions, those are decimals. But remember, decimals can be rewritten as fractions. This negative 0.7 is the same as saying negative 7/10. This 2.58 is the same as saying 2 and 58 over 100. So now we have something called irrational numbers. So irrational numbers has the word rational in it, but it has the ir in front of it. So irrational numbers are just totally different from rational numbers. They are complete opposite. They have nothing in common. So they're not going to be a subset of anything. They don't even belong to our circles where we have circles inside of circles. It doesn't even get to be a part of that because they're completely different. They have nothing in common with rational numbers. And since everything else is a subset of rational numbers, that means irrational numbers have nothing in common with any of the other numbers either. So rationals and irrational are disjoint sets. So this word disjoint means that they have nothing in common. They have no common elements. And elements are what are inside of the sets. So they have no common elements or no common numbers, which means they're called disjoint. So here are some examples of irrationals. We have the square root of 2, we have pi, we have 5 square root of 7, and we have 1.305. Whoa, and actually that ... means it's an ellipse, which means that it goes on forever and ever, but nothing is ever repeated. We have no pattern here. So these types of numbers where you have a radical that is not a perfect square, or you have an example such as pi, or this number here where our decimal never repeats, then that's an irrational. So you've got to be careful because if you have a decimal that does repeat, such as 0.33333333, well, that's the same as 1/3, which is a fraction. So you've got to make sure that when you're looking at your decimals, that nothing ever repeats, because if it repeats, then it could be a fraction. So this has no pattern to it, which means that it's an irrational. So then we have the set of real numbers, and real numbers include both rational and irrational. So we can say that the set of real numbers, which is an R with a double line, is equal to Q, which is rational, and irrational. Sometimes we write irrational as a Q and then an apostrophe, which means Q prime or not Q. So all of our rational plus all of our irrational is equal to the set of real numbers. So here is a diagram that has a set of all of our real numbers. So again, we have our rational on this side, and we have our irrational on this side. So notice how our irrational has nothing in it, just irrational numbers, such as the square root of 12 or pi or something like that. Whereas rational has our fractions, and then inside rationals we have integers, which are negative numbers and whole numbers and natural numbers. And our whole numbers have 0 plus all of our natural numbers, such as 2, 17, any type of counting number is our natural number. So let's work on classifying numbers. We want to place the given numbers and the correct set on a Venn diagram. We want to be as specific as possible when classifying. So we want to go to the innermost circle that we can get into. So let's start with negative 15. So negative 15 we know is a real number. We know that it is a rational number, and we know that it's an integer. However, it's not a whole number, so it has to stop at the integers. 0 we know is a real number. It is a rational number. It is an integer, but it is also a whole number. However, it is not a natural number, so it has to stop at the whole numbers. Then we have the number 3 over 2, which is a real number and a rational number. However, it's not an integer, so it has to stop at the rational numbers. Then we have the number 1,290, which is a real number. It's a rational number. It is an integer. It is a whole number, and it is also a natural number. Then we have the number negative 2/5, which is a real number. It is a rational number. However, it is not an integer because it is an opposite, but it's not an opposite of a whole number. So that means that it stops at rational numbers. So that's where it's classified. And then the square root of 12 is a real number. However, it's not rational, it's irrational. So it will be in the set of irrationals. So we can have questions like this. Does the following equation have a solution over the set given? And if yes, we want to solve. So 3x equals 9 over the set of whole numbers. So what we're asking is, if we were to solve for x, would we have a solution that is a whole number? So if we divide 39 by 3, would we get a whole number if we were to solve for x? Well, 39 divided by 3 gives us x equals 13, which is a whole number. So yes, if we have a solution that's over the set of whole numbers. Let's say 7y equals 48 over the set of integers. The answer to that is no, because dividing both sides by 7 produces a rational number, because 48 over 7 doesn't simplify, which means that it's not an integer, it's a rational number. So because it's not an integer, and that's what we were looking for an integer, that means the answer is no. It does not have a solution over the set of integers. It has a solution. The solution is 48 over 7. It's just not a solution over the set of integers, which is what I was asking for. All right, let's look at this symbol. This is an inequality symbol. And this inequality symbol, when we read them, we always read left to right. So we're saying something then this symbol is something. So remember, the alligator always eats the bigger number. So if we're reading from left to right, we're saying this is greater than this. So again, reading left to right, this is less than this. So this symbol means less than. Now when we put the line under it, we means greater than or equal to. This symbol means less than or equal to. And this is a symbol where it looks like an equal, but there's a slash through it. So we say this is not equal to something else. So all equations that have a variable and an exponent of 1 have only one solution. However, if you have an inequality, you can either have many solutions or no solutions. So an inequality is different than an equation. Remember, an equation can only have one solution. And an inequality can either have many solutions or no solutions. So an inequality is a mathematical sentence expressing the relative size of two quantities that may or may not be equal. So the solution set are all the numbers that make an inequality true. So which numbers are members of the solution set for the inequality 3x is less than negative 6? So what you want to do is you want to test each of those numbers and see if they make our inequality true or false. So if we were to plug in negative 5, we would have 3 times negative 5, which is negative 15. And negative 15 is less than negative 6, so that one is true. If we were to plug in negative 3, so we would have 3 times negative 3, that would give us negative 9. And since negative 9 is less than 6, that one is also true. Then we plug in negative 1. 3 times negative 1 is negative 3. So the sentence reads negative 3 is less than negative 6. That is false. So that is not a part of the solution set. Then we try 0. 3 times 0 is 0. So we have 0 is less than negative 6. So again, that is false. That is not part of our solution set. Then we have 3 times 2 is 6. So it reads 6 is less than negative 6, which is false. So it's not part of our solution set. All right, that is all we have. Go ahead and try some problems on your own.